Hello, today we will be working on chapter 16. The review is going to be a little bit different because our class got shifted into an online section midway because of the global Gremlin pandemic. That's your new classmate. He basically enrolled halfway with us, so you're going to see him for this video. Just don't mind him, he's a friendly guy, he just wants to learn with you. Okay, so let's get right into the question. So number 1, what is the correct IUPAC name for the following compound? Okay, well, for this chapter, when you're dealing with aldehydes and ketones, that's going to be your parent, okay? That's going to be what you name it after. So in that logic, keep your aldehydes and ketones on the smallest number possible. So for instance, if I label it from right to left, this would be 1, 2, 3, and 4, right? If I label it from left to right, it would be 1, 2, 3, 4, 5. The ketone would be on the 5th carbon instead of the 4th carbon. That's not good. You want your aldehydes and ketones to be on the lowest number. So let's continue counting. So 5, 6, 7, and 8. Notice that I have a 7-methyl. So already you know the answer choice. It would be B, okay? 7-methyl. But what else can we do? Well, notice that my longest chain is 8 carbons long. And since I'm working with a ketone, I know that the suffix is going to be none, N-O-N-E. So what we have here is a 7-methyl, 4, that means that there's something on the 4th carbon. What is it? 4 octanone. Okay, so that must mean that, notice that there's a none, it means that there's a ketone. Where's the ketone? The ketone is on the 4th carbon. And how long is the overall chain? 8. And on the 7th carbon, there's a methyl group. So that's what you know about 7-methyl-4-octanone. Number 2, a correct name for the following compound would be which of these below? Okay, well, notice that we have an aldehyde now. So you're going to start counting directly on the carbon from the aldehyde. So we go 1, 2, 3, 4, 5, and 6. Right. So on the 2nd carbon and on the 5th, there is a methyl. So we have 2, 5. We have 2 methyls, so that's going to be dimethyl. And what do we have? Well, we have an aldehyde. And aldehydes have al. So al is going to be for aldehyde. Aldehyde. Okay. So overall, our longest chain is 6 carbons. So we have 2, 5 dimethyl, hexane, al. Okay. So the al means that there's an aldehyde. Where is it? Well, the aldehyde is on the 1st carbon, so we can ignore the number. There are 2 methyls. One methyl occurs on the 2nd carbon and the other occurs on the 5th carbon. Okay. So what is the correct structure for 3-phenylpropanol or propanol? Well, I like to draw these out. So we have right here a 3-structured carbon. Okay. So prop is 3. So we go 1, 2, and 3. Okay. And then we have al. So somewhere on this 3-structured carbon, there's going to be an aldehyde. Well, where is it? Do you see a number? Well, no, you don't see 3-phenyl-2-propanol. No. So if you don't see a number before propanol, you can assume that the aldehyde is on the 1st carbon. So let's just arbitrarily make this the 1st carbon. Now on the 3rd carbon, we're going to have a phenyl group. So 1, 2, 3. So 1, 2, and 3. Let's make a phenyl group. So let's do this. We have, if I can draw this correctly, I probably can. So let's do this guy. I hope you're having a great day, by the way. You know, stay sanitary and whatnot. So that's the best I can do. So that's a phenyl group. Now what resembles this structure? Let's see. Now it would have to be 2, right? It would have to be 2 because here's our phenyl group. Here's our phenyl. There's our propyl group. So we have 1, 2, 3. Hold on. No, my mistake. I was looking at it wrong. This would be the correct answer, number 5, or E. So, again, my mistake. We all make mistakes. I'm learning it with you. So, here we go. Here's an aldehyde. This is why you always got to verify your pictures. So, here's an aldehyde. We go 1, 2, and 3. That's a 3-structured carbon, or molecule. So, that's going to be a prop. And here's our phenyl group. Here's our phenyl group right there. And that is the correct answer choice. Oh, there we go. So again, phenyl is just a benzene ring directly attached to a carbon structure. Okay? So, not bad. Now, lithium aluminum hydride cannot be used to convert carboxylic acids to the corresponding aldehydes because of what? Because of what? Well, lithium aluminum hydride is very, very strong, okay? It's super strong. So it doesn't make sense that A would be correct. A is wrong because it's saying that it is weak. It's not sufficiently reactive. This is wrong because lithium aluminum hydride is very strong. Okay? Well, the answer is kind of weird, but the answer would be C. You need to know that carboxylic acids, okay, so carboxylic acids, when you treat it with lithium aluminum hydride, will convert into a primary alcohol. And how does that reaction occur? Well, it's a very, very messy reaction. So I'm going to clear some room and we're going to do it together. So to begin this reaction, first the hydrogen breaks off from the aluminum. And since hydrogen is more electronegative than aluminum, when the bond breaks, it breaks towards the hydrogen, creating a hydride. And where are we going to attack? We're going to attack the oxygen that has the hydrogen, because this hydrogen right here is acidic. So he is going to break off, and they are going to pair together. So we now have R, O, a double bond with the oxygen, and this is negative, so it's an alkoxide. And we also have aluminum with 3 hydrogens. And to stabilize the structure, we have a lithium right next to it. Of course, we have H2. So what happens now? What happens now is that this bond right here breaks towards the oxygen. And another hydrogen breaks off from the aluminum. Since this bond right here broke, this is more negative. And since we made a negative, we have to make a positive, right? So this carbon is positive now. Of course, this aluminum right here is now positive as well. Notice that we went from a negative, we lost a hydrogen, so it was neutral, and then we lost another hydrogen, so it became positive. Okay, so the positive aluminum is going to be attracted to the negative oxygen. So here we go, towards the aluminum. So we now have this structure. Oh, and the hydrogen is going to be attracted towards the carbon. We have R, oxygen with the lithium, another oxygen with an aluminum, with 2 hydrogens, of course, and we have a hydrogen as well. Now, this structure can actually do some weird stuff. Notice that we have a lot of electrons on this right carbon, or oxygen. Well, what happens is that these electrons can actually make a double bond between the carbon and the oxygen, and when it does that, carbon is going to have 5 bonds. 1, 2, 3, 4, and 5. 5 bonds. It doesn't like that. So it's going to shoot off this oxygen. Okay, and a double bond right there. And we have hydrogen. So that is an aldehyde. And you're probably saying, hey, Brian, you said that we couldn't make an aldehyde from lithium aluminum hydride with carboxylic acid, but here we are, we made an aldehyde. Well, yeah, and Mr. Gizmo also agrees with you, but he realized that, hey, lithium aluminum hydride is going to react with aldehyde because we are in a solution with trillions and trillions of lithium aluminum hydrides. So another lithium aluminum hydride will see this aldehyde and react with it further, and it will actually oxidize it even more. Okay, so what do? We now have this right here, so let's clear the screen real quick. So now what happens between a new lithium aluminum hydride is that the H breaks again, making this one a hydride, so it's a negative hydrogen. This bond can break towards the oxygen, making this one negative and making this carbon positive. The positive carbon is going to be attacked by the hydride. We now have this structure. Okay. Well, now what you can do is an acid workup. So let's try to do with hydronium. So hydronium is going to do what? It's going to donate a hydrogen because it's an acid. So it donates a hydrogen. Oh, that's a very bad H. My gosh. So it donates a hydrogen to the oxygen, to the alkoxide. And what we have now is basically a primary alcohol. Of course, you can ignore the hydrogens if you want, but we just made a primary alcohol from a carboxylic acid using lithium aluminum hydride. And that's why we don't use it, because first you're going to have an intermediate as an aldehyde. Yeah, but it's not stable because it's going to be reacting with lithium aluminum hydride in the solution. And when it does, it's going to convert it into a primary alcohol. So on your notes, just know that pure lithium aluminum hydride will convert will convert carboxylic acids into primary alcohols. All right. Number 5, identify the reagents that would bring about the following reaction. So I drew it out for you, and we're working with what's called an acid chloride. It looks like an aldehyde, but instead of the H, you just have a chlorine. And it's really good for Friedel-Crafts reaction if you recalled it from chapter 15. This would be called an alkylation reaction. But basically, you're converting an acid chloride into an aldehyde. But how do we do that? Well, you need to know that lithium aluminum hydride will work. And you're probably wondering, hey, you literally said like 2 seconds ago that it's not going to work. Yeah, I did, because I said for pure lithium aluminum hydride. This is not pure lithium aluminum hydride. This is actually a special one. It's like a bigger, bulkier version. It's lithium, aluminum, and then it's kind of like this weird one. It's like T-butyl oxide, T-bioxide, with 3 of them. So imagine like a tert-butyl with oxygens, and there are 3 of them on this aluminum. Right? So it's just like really, really clustered, and it's very sterically hindered. So what this allows us to do is that it will allow us to kind of isolate the intermediate of an aldehyde. So you remember the last reaction where we had an intermediate aldehyde, and then it immediately reacted with another lithium aluminum hydride to create a primary alcohol? Well, in this structure, or in this problem, if you're losing T-butyl oxide with lithium aluminum hydride, then the intermediate structure is going to stay pure. Nothing else is going to react with it because it's so sterically hindered. It's not going to be able to do it. So we can actually isolate the aldehyde. So it's kind of like a weird reaction, but it's basically the same thing. We would still have kind of like this hydrogen that would come in and take out this oxygen, or well, not this oxygen, sorry. So first of all, this chlorine would leave, it would pair with the lithium. We have this positive carbocation oxygen, right? So this electron can go and make a triple bond for like stability. And then it could go back into the oxygen. So it's kind of weird how it reacts, but basically there's a positive carbocation right here. A hydrogen or a hydride comes in, attacks it, and there's your aldehyde, okay? So the take-home message is that lithium aluminum hydride with tert-butyl oxide will allow us to make an aldehyde intermediate and make it stay pure. This can also be done with diiso aluminum, hold on, sorry, what was it? It was diisobutyl aluminum hydride. So if you see something like that, it's gonna react the same way, okay? It's gonna allow you to make an aldehyde. So that's it. So the answer is C. Of course, see, E would be wrong because lithium aluminum hydride is too strong and it's going to be really reactive. C is like a watered down version of it, and it's going to allow us to do the reaction. So it's cool. So dissolving benzaldehyde in methyl alcohol establishes an equilibrium with what compound? So benzaldehyde is this compound. We have an aldehyde structure, so there's a carbon right here, a hydrogen, and this guy. And then we're going to be reacting it with methyl alcohol. It's kind of like a little fun reaction, I would say. So here's a methyl alcohol, right? And let's see, 2, 4, 6, 8. So what we can do here is that this bond can break towards the oxygen, making this one negative and making this carbon positive. Now, the oxygen right here from the alcohol is going to be really reactive towards this carbon. Okay? So we now have a benzene ring. And here's my hydrogen. Here's my alkoxide. And here is my other oxygen. So here's my alcohol and a methyl. Okay, so yeah, what we can do now is that we can actually protonate this oxygen right here. This hydrogen can leave the oxygen, and it can actually be picked up by this oxygen. Sorry, so we can have this benzene ring. Right there. And let's just do kind of like an oxygen right here, the methyl. We have an alcohol. So, of course, there's still a hydrogen right there, but we can ignore it if you want. Right here was the alcohol, but the hydrogen left, and here's the methyl group that was originally attached to the alcohol, okay? So that's all that happened. Now we have to go into the answer choices. So answer choice A, whenever you see C6H5, that's just a benzene ring, okay? So imagine like a benzene ring attached to this carbon. So this carbon has a benzene ring to it, and on this carbon there's an alcohol, right? Okay, and on this carbon is a hydrogen as well. So that makes sense. And then there is oxygen. And then on that oxygen is a methyl group. So it seems to me that the correct answer choice is A. So the answer choice would be A, okay? All you had to do was realize that this oxygen can be a withdrawing group. It's a very famous withdrawing group. It can withdraw electrons, making it negative, making the carbon positive. The oxygen can then react with the carbon, and then it can shoot off the hydrogen because it's acidic, and the hydrogen can go towards the other oxygen, right, making an alcohol. So that's pretty cool. Let's move on to question 7, and let's make some room. So let's do this. Okay. Selects the structure of the major product in the following reaction. So we have a ketone, and we have this weird looking thing. What is that? Well, let me draw this out first. So this compound right here is going to be a peroxy acid. Okay, so this is a peroxy acid. Right? And the overall reaction is a very famous reaction called a Baeyer-Villiger. A Baeyer-Villiger reaction. Okay? And it's German, so you have to have like a German accent whenever you say it. But it all begins with an acid reacting with this ketone, right? So let's do kind of like I guess, hydronium. So let's do hydronium. And it's going to give up one of its hydrogens to the oxygen, okay? So here's what happens. This bond breaks towards the oxygen, making this one negative, and making this guy positive, a positive carbon right there, okay? And now this oxygen is going to pick up this hydrogen that was left. So let's kind of do that. So now we have this structure. An alcohol right there. And of course we still have a positive carbon. And what happens now is that in this compound for the peroxy acid, this is where the reaction begins, okay? This hydrogen is going to leave the oxygen, okay? Well, actually it's not going to leave the oxygen, I'm sorry. The oxygen itself is going to be attracted towards the carbon since it's positive. So now we have this weird structure. This is an oxygen, another oxygen. Here's a double bond right there. And of course this one still has a hydrogen. But this oxygen doesn't like that, right? It doesn't like it a lot. And well, if you were to do your Lewis structures or numbers or whatever, you would notice that this oxygen is positive. It doesn't like that a lot. So instead, what it does is that it's going to deprotonate. This hydrogen is acidic, so it's going to deprotonate towards the oxygen, right? Okay. Oh, and we still have a methyl group. Sorry. All right. So what happens now? Well, now we have this structure. And of course, it's a very long and arduous reaction, right? So I'm only going to do it once because it takes a long time, okay? So here we go. Okay, so now we have that reaction, or that structure, sorry. So what do we do now? Well, notice that we had a water right here, right? Since the hydronium deprotonated to become water, this water is going to attack the hydrogen that was left, forming the acid again. And now that's going to be important because this acid is going to react with this structure, right? And we're going to do the same thing. We're going to do the exact same thing. This bond is going to break towards the oxygen, making this one negative and making this carbon positive. Now one of the hydrogens can break towards the oxygen, or yeah. So let's see here. Actually, yeah, so one of the hydrogens is going to break towards the oxygen. It's going to be picked up by the oxygen right there. And what else happens? Well, what happens now is that we have an alcohol right there. And before I clear the screen and continue the reaction, I just want to draw out what we have, okay? So we now have an alcohol right here. We have a methyl. And then we also have an oxygen attached to another one. Here's an alcohol. And we have a what? We have water. So this is not really good. This is very sterically hindered. You have a lot of oxygens attached to one another, and they're really close to each other. So they're going to be like very, kind of like, unenergetically favored. It's not good. So what can we do now? So what happens now is that the hydrogen on this alcohol can break towards the oxygen, and the water can take the hydrogen that was left behind. Afterwards, you're going to have a lot of electrons around this oxygen, so it's going to break towards this carbon bond, making a double bond. Now, can you see the problem here? Right? So the problem here is that this carbon is going to have 5 bonds, and it's not going to like it. Okay, it doesn't like doing that. So what happens now is kind of like a weird reaction. Okay, it's a very, very weird reaction. And, well, I should probably kind of like label it, It's going to be really weird. But let's just do it, okay? Let's make this right here. Okay, so what happens now is that we are going to actually transfer a whole carbon. We're going to transfer an alkyl to this oxygen. Okay, so this oxygen is going to break right here directly on this oxygen, okay? And then this bond is going to break towards this oxygen. And then these electrons are going to make a double bond, okay? So you can kind of see what this structure makes. That structure made a carboxylic acid, okay? But let's go back into the structure. What do we have? Well, what do we have now is an oxygen directly attached to another oxygen. We have this compound, right? And what else? We have a direct linkage right there. Boop. And we also have this carboxylic acid. Should do this right here. It's so weird how it's drawn, but it's like this. Okay, so that's basically the structure that we have now. So let's verify that this is correct. Let's do 1, 2, 3, 4, 5, 6. So we should, yeah. So I'm missing a carbon, but it's kind of like the same structure, almost, right? There should actually be a carbon right here. But essentially, we moved an alkyl. And this alkyl is called a migration aptitude. So this is the migratory aptitude. Okay, migratory aptitude. So it's when you're moving an alkyl onto an oxygen, directly onto an oxygen. And this is really bothering me, so I'm going to just label this right here, because technically that's not right. So technically there's a 6th carbon right here, and there's a methyl group on that 6th carbon. Okay, so it's like 1, 2, 3, 4, 5, and 6. You see? So I just kind of drew it incorrectly, but anyways. So whenever you move an alkyl directly onto an oxygen, you're doing a migratory aptitude. So it's like a methyl shift almost, but to like an extreme process. And basically, you're going to have problems that has an oxygen on the left side or on the right side of a structure, and which one is correct. Well, you can tell which one is correct via this kind of like flow chart, I guess. So first, hydrogens are going to be very reactive, very favorable, and then phenyls are going to be favorable. So phenyl is going to be favorable, then a tertiary alkyl, secondary, and then a primary. So these are going to be alkyls. Okay. So notice that this is only because of the carbocation formation. That's how I like to see it. Okay, it may not be correct terminology, but that's how I see it. Because if we were to delete this bond right here and instead put like a carbocation, Well, technically you have a secondary carbocation, and that's going to be more reactive than a primary carbocation, right? So if I did a primary carbocation, then I would have my oxygen on this side, right? I would have it on that side, which is not correct, because a secondary is going to be more reactive toward for migratory aptitude. So a secondary is more reactive for migratory aptitude and not a primary. You're going to see that kind of like thought process on the next question, I believe. But yeah, so that was a very intense reaction, but this is the main takeaway for this reaction. So for Baeyer-Villiger reaction, you should know that hydrogen is more reactive than a phenyl. A tertiary is more reactive than a secondary, and a secondary is more reactive than a primary. Okay? And you want your added oxygen, your ester, to be closer to the area with the most reactivity. Okay, so in this case, my ester was closer to the area with the secondary carbocation. So for number 8, select the structure of the major product for the following reaction. Now you're probably saying, okay, well, I know this. You know, clearly the answer is 2 or 4 because of an ester, right? So you'd probably be thinking it's 4, right? But it's wrong. Why is that? Well, of course, this is a Baeyer-Villiger reaction. And this is with an aldehyde, not a ketone. Okay, so whenever you're doing a Baeyer-Villiger reaction, whenever you're dealing with ketones, they're going to give you an ester. But when you're reacting with aldehydes, they're going to give you a carboxylic acid. Okay, so there we go. So they're going to react to give you a carboxylic acid. So which of my answer choices have a carboxylic acid on them? Well, 4 is wrong. That's an ester. And 5, that's too many bonds, right? That's too many oxygens for that. Okay. There is no carboxylic acid right there. And this is kind of a weird one. You know, I've never seen a structure like that. Unless you're working with like a proxy acid. But that's kind of weird. So no, that's not even a proxy acid. So the answer would have to be A. This is a carboxylic acid, and technically you just added an oxygen right there. All right, it's a very complicated reaction, but MCPBA, metachloroperoxybenzoic acid, is a very common proxy acid, and if it reacts with this aldehyde, it's going to create a carboxylic acid. Okay, so if you're reacting with a ketone with a peroxy acid, you're going to get an ester. But if you're reacting with aldehydes, you're going to get a carboxylic acid. Okay, so that's kind of the takeaway for that problem. Now for number 9, now you're working with a ketone. So you should know the answer, or at least what it should look like. You should be saying, okay, well, Brian and Gizmo, the classmate, Gizmo said that, hey, whenever I have a proxy acid and a ketone, I should be expecting an ester. So there should be no carboxylic acids or anything with alcohols. So that's wrong. That's an aldehyde. I don't see how we got an aldehyde. That's kind of like a carboxylic acid on this structure. Not good. So now we're working with esters. It's either between 1 and 2. Okay. Well, which one is it? Am I going to pick the first one or the second one? Well, I'm going to pick the second one. Why is that? If we were to delete this structure right here, if we were to delete this, and we were to delete this carbon right here, right? Or I guess this carbon, what would we have? It's kind of like my logic. I know it's not the correct way to think about it, but it's how I think. If we were to do this, well, what do we have? We have a secondary carbocation. And over here, we have a primary carbocation. And which one am I going to react more with? I'm going to react the most with the secondary carbocation. Okay? I'm going to do that. And so I'm going to add the ester on the side with the secondary carbocation. Because again, the reactivity goes in this way. So phenyl is going to be the reactive, then a tertiary, then a secondary, and then a primary. So between the primary and the secondary, I'm going to pick the secondary, okay? So whenever you're doing Baeyer-Villiger reactions with ketones, you're going to make an ester. And then you're going to add your oxygen, the ester oxygen, to the side that gives you the best carbocation. So in this case, if I add it on the left side, I'm going to get a secondary carbocation, which is great. If I add it on the first side, or the right side, on this one, I'm going to get a primary carbocation, and that's really bad. It's not good, it's not reactive. So the answer choice should be B. Okay, for number 10, what is the final product Z of the following synthesis? Okay, well, first, we're going to have to notice that this is toluene, and we're reacting it with some potassium permanganate with alcohol and heat. Well, this is always going to make a carboxylic acid. You can do it in nitrile groups, aldehydes, ketones, etc. It's going to make a carboxylic acid. So I'm going to call it carboxylic acid. And we now have this structure. Let's see. Right here, an oxygen. Okay, now we're reacting it with thionyl-chloride. I call it Sokol. So what Sokol does is that it's going to do this. It's going to make this chlorine. Well, first of all, this bond breaks towards the oxygen, making the sulfur positive. This oxygen is going to pick up the sulfur, and the chlorine breaks. Afterwards, you're going to have kind of like it's not water, but it's similar to water in the fact that oxygen has 3 bonds to it. And that's not really favorable. So what am I doing? Right there. Here we go. So it has a sulfur and some chlorines. Actually, this chlorine left. So here's my chlorine right there. This water, or it's not water, but it acts like water. So this oxygen has 3 bonds. It's positive. Whenever an oxygen is positive, it can leave. So this one can leave, right? And of course, you're going to have kind of like this weird structure. I guess it's important for you to know that the lone pairs on this oxygen can break, making a triple bond. And it just stabilizes it until it needs to react. Whenever it wants to react, it's going to go back towards the oxygen and become a double bond, okay? So let's just say that it's immediately reacting, okay? So whenever this leaves, you're going to have a positive carbon right there. The chlorine is going to attack this carbon. Okay? There you go. So that was Sokol. If you just want like a shorthand reaction, then just realize that Sokol is just going to take out the alcohol and replace it with a chlorine. Okay, so this is very important because we made an acid chlorine. So we made an acid chloride. Okay, which can be used for Friedel-Crafts reactions and other reactions. We will now be using lithium aluminum hydride tri-tert-butyl oxide. Okay, so there are 3 tert-butyl oxides on this lithium aluminum hydride. And what do you know about that? Well, this one is so big and bulky. Okay, big and bulky, that it will allow us to kind of isolate the aldehyde intermediate. Okay, so it's going to give aldehydes. I really like this color. Anyways, so now this acid chloride is going to completely react with lithium, aluminum, and let's call it T-butyl oxide right there. And this whole thing is just going to become an aldehyde. Okay? And of course, you can do it with diisobutyl lithium aluminum hydride. Diisobutyl aluminum hydride. You can do that as well. Which looks like this. Okay, you can do that. It's fine. But basically, it just becomes this. Okay? So diisobutyl aluminum hydride and lithium aluminum tributyl oxide, right? Whatever, I don't care. They do the same thing. They're going to make an aldehyde in the very last reaction. So what is my answer choice? Well, this one doesn't make any sense because you're adding the aluminum to the oxygen, right? And you have too many oxygens, so bad. This one is a carboxylic acid. They just stopped at the first structure or reaction. Bad. This is okay right here. Wait, oh, I'm sorry. This is an ester, so this is the carboxylic acid, so they stopped at the first structure. Bad. They added a lithium to the oxygen. That's also bad. And so the answer choice should be 3. That is an aldehyde that was formed from the very last reaction. So that's the take-home message for that one. Okay, number 3. So let's clear the board and we'll pick up. Number 11. Select the structure of the major products of the following reaction. So the first reaction is going to be potassium permanganate with alcohol, and it's very hot. Okay, so you're probably wondering if it's going to be a carboxylic acid. Not necessarily. Okay, not necessarily. What happens here is that you're going to actually cut the double bond in half. So what I like to think of is like the hot is like a very hot laser, and we are directly cutting this compound right there. Okay, so what happens now is that we have a cyclopentane with a cut alkene. Okay, so it's cut. Let's do this. And this is like a Ochem 1 reaction. Kind of weird that it would be brought up again, but here we go. Essentially, you can just add an oxygen right there and an oxygen right here. So you made a ketone, which is very useful in this chapter because we can do a lot with ketones. We can do a lot of reactions and synthesis problems. But that's all there is to it. If you have hot permanganate and some alcohol and heat, we can actually cut the double bond in half and add an oxygen to it. Okay, so you oxidize it or something. So this is really good. It's going to be number 5. So this is the correct answer choice. Number 12. What would be the product for the following reaction sequence? Okay, so hey, this is what I was talking about. We have diisobutyl aluminum hydride with some very cold temperatures. Okay, so what do we do? Because we're reacting with esters. Okay, well, when you're reacting with esters, it's kind of weird, but let's ignore the structure right here. Let's ignore that. What am I going to get from this ketone? Oh, you said that we're going to get an aldehyde. Okay, I agree with you. We're going to get an aldehyde. But afterwards, what else are we going to get? So my answer choice should have an aldehyde in it. So number 1 is wrong. Number 2 is wrong. Number 3 looks okay. Number 4, why do we have a ketone? No, my ketone is supposed to be an aldehyde. There are no ketones. Okay. Number 5 is an aldehyde. Okay, so that's cool. So what's the difference between 5 and 3? Oh, wait. 5 is actually a carboxylic acid, so that doesn't make any sense. So just by knowing what to expect in your answer choice, you can eliminate all of them. Okay, so diisobutyl aluminum hydride is always going to give you aldehydes. Okay, it's going to give you aldehydes if you're working with ketones. So there you go. Pretty cool, right? And basically, you're going to get an aldehyde right here. And then you're going to have a negative oxygen, an alkoxide. Well, the acid workup comes from the water. Let's pretend that this is hydronium. So let's say it's H3. Well, the hydronium is going to donate a hydrogen, and it's actually going to give it to the oxygen, making an alcohol. So this is going to be carbon 1, 2, 3, 4, and 5, right? Also, this ring broke. Okay, so now it's just like a alkane. So over here we have 1, 2, 3, 4, 5, and of course you have 6. So 6. So the alcohol is going to be on the 5th carbon, which makes sense. Okay, so again, diisobutyl aluminum hydride and the weird lithium aluminum triterpbutyl oxide. It's going to give you aldehydes. So remember. So number 13, the product J of the following sequence of reactions would be what? All right, well, whenever you're reacting with aluminum trichloride, all that happens is that this chlorine leaves and it makes aluminum tetrachloride or tetrachlorine or whatever. And then let's arbitrarily pick this bond, this double bond. It's going to take this positive carbon, right? So it's going to take this positive carbon right here and it's going to make this. Also notice that Gizmo is enjoying his little snack. He looked hungry. So he got like a double pounder, you know, and some fries, which is fine. So let's do that right here. Actually, let's do. So we're attached to this oxygen directly, and then we have a carbon, and this carbon has 2 carbons on it. Okay. So now we have this structure. We are now reacting it with a peroxy acid. More importantly, it is metachloroperoxybenzoic acid. Okay, so it's just going to be a what? A Baeyer-Villiger reaction. Okay, so what do you know about this reaction? Well, this reaction is going to make an ester because notice that we are reacting with a ketone. So a ketone is going to give you an ester. If we were reacting with an aldehyde, we would have a carboxylic acid, okay? But since we have a ketone, we're going to get an ester. So where am I going to add my ester? Am I going to add it here, or am I going to add it here? Well, the way I like to think about it is, you know, well, what if I broke my bonds, right? And I added a carbocation. Well, this is going to be secondary carbocation, and this is going to be a weird one, but you're probably thinking, okay, well, this is bad because this would be a vinyl carbocation, and I know that vinyl is terrible and it's not going to react. Well, you're right, but this is kind of like topsy-turvy. It's kind of weird, but this would actually be a phenyl carbocation. Okay? And it's going to react more, so it reacts fast because the kind of like order is hydrogen is faster than phenyl, and that's faster than a tertiary alkyl, and it's faster than a secondary, and it's faster than a primary. So phenyl is going to be more reactive towards the formation of an ester than a secondary alkyl. Okay, so where am I going to put it? Well, number 1, there's no ester. Number 4 is just weird. That's an epoxide. That's bad. Now it's either between 2 or 3. Well, over here, they added it to the secondary carbocation, so that's bad. You want it to be near the phenyl group, okay? So it's going to be number 2. Number 14, the product E of the following sequence of reactions is what? Okay, well, right here we have PCl5. All that's going to do is make this into a chlorine. So that is a chlorine now. So this is a formation of an acid chloride. Then we're treating it with aluminum trichlorine, I guess, which we just did. Is just going to make this whole structure into a positive carbon right there. And then we're going to be reacting it with this compound. So what happens now? What happens now is that we are going to be adding, basically, it's kind of weird to think about it, but we're adding it to this structure. Okay. Whenever I add it, where am I going to put it? Am I going to put it here, or am I going to put it here? Well, I'm going to put it on this carbon right here. Okay? because that's going to allow me to have kind of like a lot of resonance, I guess, but also it's kind of like a Markovnikov reaction. There are 2 hydrogens here and there's only 1 hydrogen there. I'm going to put it to the area with the most hydrogens. Therefore, I'm going to have a stable carbocation. Okay, so I'm going to have it here, and then carbon, carbon. Okay, so that was step 2. Now step 3 is kind of the weird one. That's a weird one. Well, this right here is referred to as a thioacetal, right? So this is a thioacetal. And we're going to have kind of like a mini lesson on what an acetal is, and I'm going to bring its brother, the hemiacetal, and show you the difference between those two, okay? But what happens here is that whenever you react specifically with some sulfurs, so we have 2 carbons right there, well, what happens here is that we're still going to have our benzene ring, okay? And all that happens is that now we're going to have some sulfurs, and they're going to be connected to each other like this. Okay, notice that we still have our carbons, 1, 2. Okay, that comes from this carbon, 1, 2. And then if we react it with an acid, such as BF3, or in simpler cases like water or hydronium, well, what happens now is that you're going to remove the added S's, right? And the carbons. So we have this structure right there. And we just have carbon, carbon, carbon. So what happened here is that we removed this whole structure right there via a very complicated reaction, okay? So all you need to know is that whenever you're reacting with thianoacetal and then you mix it up with some Raney nickel, that's what the nickel's doing. The nickel's allowing this process to occur. It's kind of like a facilitator, like a catalyst almost. But whenever you see your Raney nickel, you just know that your ketone is going to disappear. Your aldehyde is going to disappear. And all that's going to be left is the base, okay? Is the base. So it's going to be 1, 2, and 3. So we should have 3 carbons left over. Let's see, 1, 2, and 3. Okay, well that makes sense. We have 3 carbons left over. Right, so I shouldn't have any ketones, I shouldn't have any aldehydes. No double bonds, right? Specifically for this case, right? You don't want that. These are okay. You know, the double bond between inside the benzene ring is alright. It's fine. Right here, this is weird. You have an empty gap right there. That's bad. It should be right next to the methyl group. Okay. Right here, you have like some rearrangement. That's bad. And over here on number 3, this is good. So we have 1, 2, and 3. So this should be the correct answer choice. Number 3 should be correct. So let's talk about acetals and hemiacetals and what they are. So an acetal is basically, it's easier if I show you in person, or not in person, but in an example, okay? So let's kind of imagine this thing right here, right? So an acetal is basically a carbon that has 2 oxygens attached to it, okay? So notice that this carbon right here on the center has 2 oxygens to it, but most importantly, it has an alkyl on it. So it looks like this. It looks like this right here. We have a carbon, we have an OR group on it. An OR group. So that's an acetal, okay? That's kind of important. However, a hemiacetal, so a hemiacetal is kind of like a half an acetal. So a hemiacetal is going to be this. I'm just drawing it in kind of like a cyclic compound because it's easier to see it. But for this one, it's basically an alcohol. It has to be an alcohol and an OR group, okay? And it's leading up to the same carbon, okay? So a hemiacetal is different because one of the OR groups is an alcohol, okay? So that's kind of like what you can get from these two reactions, or from these two compounds. And of course you can do it by doing a 1,2-diol reaction. So 1,2-diol can be used like this. Okay. And we can also do kind of like a thioacetal, so it's the same thing. Notice that they are synonymous. Notice that they have 2 carbons and 2 hydrogens directly attached to the oxygen or sulfur. Okay, so if you see this compound right here, or this one, just know that this may be an acetal reaction. Okay, also known as, well, it's just an acetal reaction. Okay. Now, the reason why we do this, the reason why we make acetals in the first place, is because they're very stable and basic solutions. And if you wanted to, you can actually convert the acetal back into an aldehyde or a ketone with acid. Okay? And sometimes when you're in the lab, you can use acetals to protect your aldehydes and ketones from other undesirable reactions, such as a Grignard reaction, right? So if you're trying to do like a reaction that has a Grignard, but you want to protect your ketone, you can make it into an acetal by adding a 1,2-diol, and that's going to protect it, and then you can put your Grignard. Okay, so that's something you can do. Number 15. What is the major product of the following reaction sequence? So the first one is known as a hydrocyanide reaction. So this is the hydrocyanide. Reaction. So what happens here is that the HCN, it breaks off towards the carbon, and this oxygen breaks the double bond towards the oxygen, making this one positive and this one negative. He picks up the hydrogen. Okay, now this carbon is negative because it lost a hydrogen, so it's going to attack this carbon right here. So now we have a cyclopentane, right, with an alcohol and a cyanide on it. Now, that was the hydrocyanide or cyanide reaction. Okay, that's it. That's fine. That's a reaction that you need to know. Okay, but the second reaction is lithium aluminum hydride. What happens there? Well, I can tell you that you're not going to make a double bond. Okay, so this is not right. And you're actually going to be adding things to it. You're going to be adding hydrogens to this bond, or to the cyanide. So let's kind of like shorten it. Instead of writing lithium aluminum hydride like all the time, let's just have some hydrides. Okay, let's have some hydrides. Well, this carbon is neutral, but if I put this double bond, or if I break a bond towards the nitrogen, I'm going to have this carbon being positive. Well, this carbon is going to be attacked by this hydrogen. So let's do that. Right, and that's a very bad cyclopentane. So now we have a carbon that's double bonded to a nitrogen, and this nitrogen has 2 lone pairs. So nitrogen has 5 valence electrons. 5 minus 4 is 1, and 1 minus 2 is negative 1. So that's negative right there. And we have a hydrogen. Okay, well, what can we do now? Well, we can add an acid, which is what we're going to do. So we're adding hydronium right here. Okay, we have hydronium. And it can donate this proton to the hydrogen, or to the nitrogen. Okay, so this nitrogen can pick up this hydrogen, and it's going to be neutral again. Okay, so it did that. But what if I did this again? Well, that would be positive, right? It would be positive. And what would happen? Well, this nitrogen can actually take this hydrogen again, making that into kind of like a basic solution. So we would have this compound right here. Right? And I mean, it seems alright actually. So looks weird, but this carbon is still positive. How do I get rid of this positive hydrogen or carbon, right? Well, you could do with another acid, which is fine. So this hydrogen can be donated, and this carbon, well, actually, no, because that would be negative. Okay, well, what about lithium aluminum hydride? Well, lithium aluminum hydride can be reacted again, since there's a lot of it. You have Al, blah, 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 right? This hydrogen can leave, and it's going to attack the carbon. So basically, pun intended, we have an alcohol on this carbon with 2 hydrogens, and then nitrogen with 2 hydrogens. There you go. And that's your answer choice. So right here, it would be number 3. All I did was first I did a hydrocyanide or cyanide reaction, which allowed me to have an alcohol and an added cyanide. So this would be reaction 1, okay? So that's what I have. And then I start putting hydrogens and hydrogens into the system, which allowed me to have 2 hydrogens right here and an NH2, so an amine added to it, okay? Which is a great donating group, if you remember. So this would be great. This is number 3. Over here, number 4, you don't have a nitrogen, you don't have your cyanide, so that's bad. I don't know how you made a carboxylic acid. That's bad. Okay, so number 3 would be the correct answer choice. Number 16, the product H of the following reaction sequence would be what? Okay, well, I already know this, but this is an Ylide, okay? So we're going to be forming an Ylide, which is this right here. So an Ylide is part of the Wittig reaction. This is part of the Wittig reaction. And here's how we do this reaction. After this problem, I'm going to explain what Ylides are and how to make them via 2 reactions, okay? And why we do them. So right here, whenever you see C6H5, it's basically a benzene ring that's attached to something. In this case, it's a carbon and then bromine. And now we have a phosphorus. Now what is phosphorus attached to? It's basically attached to 3 benzene rings. Instead, I'm just going to call it pH 3. Okay, so that means that we have 3 phenyl groups on it. Okay, so that's all we have. And what happens here is that this phenyl group, or this phosphorus, has some electrons, okay? And it's basically going to attack this carbon. So bromine leaves this carbon, making it positive, okay? And right here, this phosphorus is going to attack this carbon. Now, most typically, you're going to be working with phosphorus, okay? So it's kind of like what you're going to see in this classroom. Right there. So we have that, and now this phosphorus is going to be positive, okay? And we have 2 hydrogens. That's all we did. And also bromine is kind of like chilling out somewhere. Now we're reacting it with the Grignard reagent. And remember that Grignard reagents are very, very, very basic. Okay, so this is very basic right here. It's so basic that it's going to rip one of these hydrogens from the carbon. So one of these hydrogens is going to rip towards the carbon. And let's say that this guy picks him up. Actually, not this guy, but this carbon picks up this hydrogen. Okay, we now have this right here. Okay, and now this is your ylide. So an ylide is just a negative carbon next to a positive atom. And the atom has to be like phosphorus or some heteroatom, you know? Most commonly it's going to be phosphorus. So in this case, it's a negative carbon attached to a positive phosphorus, okay? So negative carbon next to a positive heteroatom. And that's your ylide. And the reason why we make ylides is because we can actually use them to make other compounds for later reactions, okay? So that's why we do that. So what happens now is that we are going to be reacting it with what? With this guy right here. We're going to be reacting it with a benzene ring, a carbon, another carbon, and a ketone. Okay, so ketones. Now, the ylide reaction is very complicated to draw out, but the result is very simple. Why is that? Well, here's how you basically get your answer. Right here, you want to cut this in half. Okay, you want to cut this in half. And we're going to get rid of this oxygen. We are going to put the carbon right here. So this is what you should get, okay? So what you should get, and I'm going to draw it over here, is that you should have the benzene ring, of course. This right here, right? And of course a double bond. Now what do we attach on the other side of the double bond? We attach this whole compound, and we attach it from this carbon, okay? And also this right here leaves, and we just have the hydrogen with the carbon. So we have this. This is the hydrogen. The carbon is attached to a phenyl group. So let's do that. And that's your answer. Okay. So what is the correct answer choice? Let's see. A would be wrong because it doesn't have any double bonds. So this whole reaction, so a Wittig reaction makes double bonds, so it makes alkenes. Okay, that's what a Wittig reaction does. It makes alkenes. So anything that doesn't have an alkene on it is wrong, right? So for B, we have a benzene ring attached to a carbon. Okay, that carbon has a hydrogen on it, right? Yeah. So let's do that. This carbon has a hydrogen on it. That's good. Let's see what else. Well, not B, but let's see it. Let's look at C. So C would be wrong because it has an oxygen on it. So this is bad. But B, let's see. A benzene ring attached to a carbon, right? But that carbon has two hydrogens. Well, this carbon doesn't have any hydrogens, and this carbon only has one hydrogen. So B would be wrong as well because of CH2. That's wrong. What about E? Well, we have a benzene ring that's attached to a carbon that has one hydrogen. Okay. That carbon is double bonded to another carbon. That's good. This carbon has a methyl group on it. Okay, yeah, I like this. And then that carbon is attached to a benzene ring. So yeah, it would be E. So E would be the correct answer choice. E would be the correct answer choice. Now I'm going to do the Wittig reaction later on in the video. Right now I just have to go through these practice problems. Okay, but we will be covering all the reactions later on. Okay, so the takeaway message is that Wittig reactions occur whenever you have an ylide, right? And an ylide is just a negative carbon that is attached to a positive heteroatom, such as phosphorus in this class. Wittig reactions make double bonds, so your answer should have a double bond on it. Number 17, what would be the final product? Again, this is going to be a Wittig reaction, okay? So what happens here is that we have a primary halide, and we're going to be reacting it with some phosphorus with triphenyl. This breaks towards the iodine, making this one positive, this positive carbocation, right on the carbon. Well, technically this phosphorus has 2 electrons that it can take and attack this carbon, giving us CH3 attached with a PH3. Okay, so now we're neutral. So actually we're not neutral, we are positive. Okay, now what happens is that this sodium hydride is going to be negative. This hydride is going to be negative, and he's going to take one of these hydrogens from the carbon and he's going to attack that hydrogen. We now have H2C P PH3, right? Now this is negative and this is positive. So now we have formed our Ylide. That's an Ylide formation, and we formed it via a halide reaction, okay? And of course you have your sodium paired up with your iodine. Okay. Now what we can do is we can react it with this ketone. We can react it with that ketone. Okay. So I should be expecting a double bond. What should be my answer? Well, my answer choice should be A. Why? Well, we still have our benzene ring, of course, that never changes. And we're going to have that. But my double bond is going to be attached to what? Well, it's going to be attached to this carbon right here and its 2 hydrogens, okay? So what I added was this guy, okay? Because recall that this structure right here leaves, okay? The phosphorus triphenyl leaves, and it leaves behind the H2C, okay? Or the methyl. And so this carbon right here has its 2 hydrogens, and that's all we did. So this is a benzene ring right here. It's attached to a carbon. That carbon is double bonded to another carbon that has 2 hydrogens. That's good. That very same carbon is bonded to another carbon that has 3 hydrogens. And that's great. So the answer choice should be A. All that happened is that we made our Ylide. And then my phosphorus triphenyl leaves, and it just leaves the carbon right here, highlighted in red. You add that to your double bond on the other side, and that should be your answer. Okay. So number 18, what is your reactant W in the synthesis given below? So we went from a ketone, we did a Wittig reaction, which is basically with Ylides and whatnot, and we formed a double bond with another structure. Okay. Well, we have our triphenyl, we have to make our Ylide. We have to make it. And I know that this right here is a very strong base. And so it can take a hydrogen from a carbon and it can form the Ylide. But how am I going to do that? Well, what if, well, I don't know, what if I had like a bromocyclopentane? What if? Why would that work? Why would bromocyclopentane work? Well, look at it. First of all, you have your cyclopentane right here. You have your bromine, right? And there are no double bonds. And remember that it's very similar to the last question we did with methyl iodide. It's the same thing. If you have an alkyl with a bromine, you can actually take out that, or well, not bromine, but with a halide, you can take out that halide and react it with the phosphorus triphenyl, okay? So you can do that. Here's what happens. In the presence of phosphorus triphenyl, this bromine is going to come off. This phosphorus is going to take this carbon right there. And notice that there's going to be a hydrogen right next to the carbon, okay? That's just naturally how it is. The Grignard reagent is going to be a very, 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 like, very times a million strong base. And that base is going to take out this hydrogen, making this carbon negative. Okay, so here's what we have now. We now have a carbon that's attached to a phenyl, or phosphorus triphenyl. This one is positive, and this carbon is negative. Okay, so that's all that happened. This doesn't really react well with ketones and whatnot, so I wouldn't expect it to be from a cyclopentanone, right? It's just, it's weird, okay? I don't see it happening. But it would readily react with bromocyclopentane. Afterwards, it's going to do the Wittig reaction and just add an alkane, or alkene to it. So the answer would be D. So I suppose we should do the reactions of a Wittig reagent. So there are two ways to make a ylide. In reaction 1, we're going to do it from a halide. So from halide, it could be like this. So let's just do pH 3, which is just, so we can do this. pH 3, and we're going to react it with something cool. Let's do a methylbromine, right? So we're going to do methylbromine. This can break off towards the bromine, making this one positive. This phosphorus can take out this carbon right there to make it kind of like a complete structure. So it looks like this. And now we have carbon with phosphorus, and then phosphorus with a phenyl right there. Okay. And so now this bromine is really, really negative, okay? So let's just do it right here. Right? Technically, I mean, you could do it with like sodium hydride. In fact, we should do it with sodium hydride. This hydride is going to take out this hydrogen right there. So he is going to take out one of those hydrogens, thus making it into this compound. H2C, negative, then P, that's positive, and we have pH 3. And so that is your ylide via a halide reaction, okay? But what about a very strong base, like we just saw in question 18? So from a strong base, it can be formed like this. So from a strong base, let's do it like this. Let's say that we already had our methyls right there. So let's do this. Right there. And we can add like a Grignard reagent. Okay, so like this. So methyl with the lithium. The methyl is going to be very negative, and he is going to take one of the hydrogens as a very strong base to make it into one of these. So it's like a CH4, and we now have H2C, negative, P is positive, and that's going to be pH 3. So again, you can form ylides via halides, or you can form it via a very strong base, okay? So either way, it's fine, but it's whatever you prefer. And you're going to see both types of reactions in these questions, okay? Also, it's kind of weird, but what if we didn't have the sodium hydride? Well, the bromine would actually take its place. So instead of the sodium hydride, the bromine would rip off the hydrogen in very desperate measures and become HBr. And so that would actually be the true reaction mechanism for a halide of ylides. Okay, so we can make ylides from halides if the halide, in this case bromine, took the hydrogen from carbon. Okay, so that's it. So number 19, what would be the product of the following reaction sequence? Okay, well, you know that Sokol is going to remove the alcohol to make chlorine. And afterwards, you're going to be doing a Friedel-Crafts reaction, which is alkylation. Okay, so it's like the ACl3 is going to remove the chlorine to make this carbon positive. And then you're just going to be adding your benzene to this positive. So here we go. Here's our benzene ring. And we're going to be adding it to the oxygen right there. And that oxygen has 1 carbon, 2 carbons. On the second carbon, there's going to be a methyl group. And now we're reacting it with what? If you can't see it, it's fine, but it's like this, which is a thianoacetal. Now, thianoacetal, you know that is going to be paired with the Raney nickel. And the Raney nickel is going to allow us to get rid of this ketone. And so my answer choice should just be like this. Also, there's no rearrangement on this one, so you're fine. Boop. So there we go. We have 1, 2, 3, and over here we have 1, 2, and 3. That's a very bad 2, 2, and 3. So I still have my ketone there. That's bad. I have a carboxylic acid. That's bad. I have an alcohol. That's bad. My methyl group rearranged, so that's bad. So it should be what? 5. 1, 2, 3, 4. 3, 4. Huh. 1, 2, 3. Well, I guess I missed a carbon. Sorry, my apologies. So 1, 2, 3, and 4. Yeah, my bad. Should have been like this. 4, 4. Oopsies, you know. 4, and then we have methyl group and a methyl group. There you go. So it should be answer choice 5. Now, if you feel comfortable with the lecture and you don't need any help with reactions, you could cut the video off right now. And I wish you a happy day, and be safe, be sanitary, have a great day, and remember that I'm proud of you. So if you need help with reactions, we're going to be continuing this video with just reactions. Should be kind of quick. Okay. Now we will begin the portion of lecture where we actually go over reactions and the process of how it occurs. Now I'm not going to go over like cyanohydrin reactions or some Baeyer-Villiger reactions, because we already went over those, you know. So I'm going to go over kind of like Imines, Enamines, you know, those types of things. And right now we're going to be doing ketones from nitriles. Okay, so a nitrile is a carbon that is triple bonded to a nitrogen, and right here we just have you know, an alkyl group attached to a metal. So this is actually a Grignard reagent. So this is a Grignard, and of course Grignard is going to be a very basic alkyl chain. So how does this process react? Okay, well, first of all, what happens here is that between the lithium and the carbon, the lithium is going to be really positive, making this carbon really negative. Okay? What happens if I make this bond break towards the nitrogen? Well, if I do that, then my nitrogen is going to be negative and my carbon is going to be positive, which leaves him able to be attacked by this negative carbon. So he's going to be attacked right there. And we now have this compound. So we have R, there's a carbon right there, and it's going to be double bonded to a nitrogen. Okay, and now we have 2 lone pairs. And of course we have our nitrile group, or not our nitrile, but our alkyl group. So it's going to be 1 carbon, 2 carbons, 3, and 4. 4 right there. Okay. Now, that's pretty simple, but what do we do about this substrate? Well, that's where the acid comes in. So by another process, an acid could come in, and it's going to do some weird stuff, which is really complicated. But overall, what you should be expecting is a ketone. So we have R, then we have this one. Actually, that happens right there. And then we have our original alkyl group. So it's going to be 1, 2, 3, and 4. So notice I made a ketone, but I added the alkyl group right there. So for a general reaction, we can have R, C triple bonded with nitrogen, N plus R, let's do like a Grignard reagent again. Let's do RLi, right? And we're doing this with some acid. Well, what I should be expecting is this guy. Right there. Where this R came right there. Okay? So it's not too complicated. Just realize that to make the ketone, the other added carbon comes from the base. In this case, we had 4 carbons, and so my added chain to the ketone is going to be 4 carbons, 1, 2, 3, and 4, right? So there we go. Now, this kind of brings us into like the segue. What if I instead said, what if I did diisobutyl aluminum hydride? What if I did that? Well, this nitrile, the nitrile is going to become what? Turns to an aldehyde. Right? It turns into an aldehyde. So it's not too bad. And, it's pretty good. So pretty fast reaction. Also, this works for lithium, aluminum, triterbutyl oxide, whatever. So right here. This also works. So it makes nitrile groups into aldehydes. So nitriles goes into aldehydes. There you go. Sometimes, if you really want to, you can make a diol from a ketone. How do we do that? Well, this bond can break towards the oxygen, making him negative and making this one positive. And then the oxygen from the water, or your acid, can actually, well, it would be acting as a base, but it can actually link up with a carbon. So we would have this structure right there, and we have a water. Now, one of the hydrogens from the oxygen can break off, and this oxygen can pick up a hydrogen. And we now have a diol. Okay? So, there we go. Notice that this is not a hemiacetal, it is not an acetal, because for it to be an acetal, well, both of these have to be what? Both of these have to be OR groups. For it to be a hemiacetal, one of them has to be an alcohol and the other one has to be an OR group. Okay? So this is not an acetal, this is not a hemiacetal. Now we will be talking about imines and enamines, or if I'm saying it wrong, then correct me. So the difference between imines and enamines are that imines, well, they have a carbon double bond to a nitrogen. However, enamines, they have a carbon-carbon double bond, and this carbon is attached to a nitrogen that has other things attached to it. Okay? So it's basically like a shift. So let's do like a carbon right there. Notice that the imines have a double bond between the carbon and nitrogen, but in the enamines, they have a double bond between the 2 carbons. Okay, so that's the main difference. Now we're going to go over the process of how to make imines. Okay, so this is going to be the imine process. So right here, we have a nitrogen that has 2 hydrogens on it, and it's attached to some chain of carbons. Like, who knows? What happens now is that this nitrogen is going to have a lone pair. And this oxygen breaks out, makes this negative, and makes this one positive. Now the nitrogen is going to attach to the carbon. Okay. Oop. And we're going to have this guy make some R groups. Yeah. All right, so now we have Hem, nitrogen. Oop. We have a nitrogen right here with an R group, and then we have some hydrogens. Now, what's kind of weird is that it's kind of like an intramolecular proton shift. So it's just going to donate a hydrogen to the oxygen. So this breaks out towards the nitrogen to make him negative. Let's just do that. And then the oxygen is going to pick up the hydrogen. So we have R, then an alcohol right here, then a nitrogen with a hydrogen, and an R group. Okay, and now we're going to be treating this with some acid. So what happens if I had, some hydronium? You can probably see what I'm going to do. This acid donates a proton, and this oxygen picks up that hydrogen, making it into water. Right there. Then nitrogen, R, and then a hydrogen. Now this water can actually leave, right? So it can leave, and it's going to make this carbon positive, okay? So whenever he leaves, the lone pair on this electron, and I should definitely add my lone pairs, is going to make this double bond, because whenever this water leaves, this carbon is going to be positive, okay? So now we have R, another R. We're going to double bond this nitrogen. We have a R group and then a hydrogen right there. Okay, so that's pretty cool. But notice that nitrogen is not iconic. What's iconic about nitrogen is that it's always seen in public with some electrons around it. Where are my electrons? I don't have any. So what can I do to get my electrons? I could get my water. So you remember when I had my hydronium? Well, whenever it donated the proton, it became a water molecule. Well, the same water molecule can snatch that hydrogen. And thus we reformed the acid, which is pretty cool. So that was the formation of an amine using hydronium as an acid and kind of like a ketone for the base. Okay, so I mean not a base, but as the electrophile, right? It grabs stuff. So there we go. So that is the formation of an amine. Also, if you want to undo this, let's say you made a mistake, you can just add water and it's going to go back into a ketone and it's going to give you an amine right there, okay? So this reaction is going to be for the formation of an enamine. So an enamine is something that has a nitrogen with 2 carbon chains. So remember in amines, you had NH2, and one of the R groups is attached to nitrogen. Well, in enamines, you have 2 carbon chains and 1 hydrogen. And you're going to see why this is important, okay? So notice that right here, I can break the bond towards the oxygen, making this one positive, and this nitrogen can actually attach itself to the carbon. And we're going to have nitrogen with 2 R groups and a hydrogen right there. Okay, so now what we can do is that this hydrogen can leave the nitrogen, right? So we're going to do an intramolecular proton transfer. So this nitrogen can grab the electrons, and this oxygen can attack the hydrogen. We will now have this. And notice that I'm really kind of emphasizing that there's a hydrogen right here, okay? That's going to be important. You can only form enamines if there's an available hydrogen that's next to this ketone or aldehyde or whatever you're working with, okay? So here we go. Okay, so after that, we can actually treat this with some of our acid. So if we treat this with our acid, the hydrogen can break off from the oxygen, and this oxygen can attack that hydrogen, right? And that's going to form a water, which is a great leaving group. And so you can actually leave afterwards. Let's just kind of do this. So we have H, O, and H. This is positive. Then, of course, we have our nitrogen, some R's right there. Okay. So whenever he leaves, he is going to leave a carbon that is positive, right? So you have a positive carbon right there. Let's put in our electrons. Okay. So whenever that happens, the nitrogen can actually make a double bond between the carbon, right? Because it has that lone pair of electrons. So these guys are going to swoop in and make that into a double bond. Right there. Okay. But now what happens here is that this nitrogen is positive, and it doesn't like being positive. It doesn't have its iconic electron lone pair, right? It doesn't have those lone pairs. It's kind of like seeing Beyonce, that like she's not, serving face. Yeah, it's like Beyonce is not serving face. It would be so uncommon and so weird to see Beyonce not looking amazing, right? It's the same thing for nitrogen. It's so weird to see nitrogen without some lone pairs. You don't want it to be positive. You want it to have some lone pairs. So how am I going to have it to, how am I going to get some lone pairs from this? Well, let's see. Well, what happens if I actually put some heat right here? If I put some heat. Well, we're talking about like 300 degrees or something. Well, if I did that, I can actually do some dehydrogenation. So I can actually take off this hydrogen, right? So I could take off this hydrogen, and this one is going to go here. My base is going to be the water. So whenever this hydronium gave up its proton, it became water. Okay, so now my water is going to take up this hydrogen. Okay, now we have some lone pairs. But what if those lone pairs made a double bond right there? Well, when it does that, you have a problem. So here's what we have now. And if I recall correctly, there is a carbon here, and then a nitrogen over here, and a double bond. So notice that this carbon has 5 bonds, and it doesn't like it. And also, the hydrogen disappears. So that was my mistake, you know? So whenever you have too many bonds, the nitrogen is more electronegative than the carbon. So these bonds are going to break towards the nitrogen. And thus, we can have this compound. And notice that there is a double bond between the carbons and not between the carbon and nitrogen. So this, of course, is an enamine. And that was the formation of an enamine. And now we're going to be covering the Wittig reaction. So this is the Wittig reaction. And this occurs because we have a Ylide, right? So we have an Ylide right here. And of course, an Ylide is just a negative carbon that is directly attached to a positive hetero atom. Now in this class, we are typically working with phosphorus. So phosphorus is just a heteroatom, which is just some other atom that is not carbon, and it's positive. Okay, so this positive heteroatom is connected to this negative carbon. So here's the reaction. Okay, so the reaction starts with this bond breaking towards the oxygen. Now this is very common. You've seen this about 16 times already. There's a lot of times. So this one makes it negative, this one makes it positive. Now this carbon is going to attack this positive carbon. Now recall that the pH3 is just 3 benzene rings attached to that phosphorus. Okay, so don't forget that. Now what we can do here is that this oxygen has a lot of electrons, and they can attach itself to the positive phosphorus. Okay, and when it does that, it becomes like a square. Okay, it becomes a square, and it's a very complicated name. That sounds really, really weird, but it's called an oxophosphatane. So oxophosphatane is what this compound will be called, and it's better if I draw it like this. Let's call that CH2, and it's going to be attached to this phosphorus, and this phosphorus is attached to that carbon. So it's kind of like a square, and of course we have our triphenyls, right? Now what we can do here is that this oxygen can actually leave, right? It can actually leave the compound. So this one can break towards that oxygen, right? And then this bond can break towards the carbon, right? So it makes this intermediate. So you have CH2, or I guess I can actually draw it out now. So we have CH2 with some lone pairs. And then we also have this weird structure, right? We have that. Now, let's see, 4 minus 2 is 2. And then 2 minus 3 is negative, so that's bad. But what if these lone pairs can actually make a double bond right there? Well, it can. Right? And there we go. So that should be your answer. Right? We have a carbon right here, and there are 2 hydrogens. So we made an alkene. And so the main takeaway message is that the Wittig reaction can use Ylides and attack ketones or aldehydes to create double bonds. Okay, so we're going to make an alkene at the end of it. Now there are multiple ways to make Ylides, and I covered that in the previous segment of this video, so you can look at that again to find the formation of Ylides, but they're not too bad. And the most common Ylide is going to be with phosphorus, which is just a positive heteroatom in this case. And these are particularly useful if you want to create other reactions. So for instance, we can do a bunch of reactions with this alkene, or it can just be like a stabilizing group. Either way, it's pretty good. Now, sometimes you might have a question on the exam, and it's saying, why is it that aldehydes are more reactive towards nucleophiles than esters? Why? Well, let's pretend that we have an ethyl group, right? So we have an ethyl group that's going to be acting as a nucleophile. Well, when we do this, we can add the nucleophile directly onto this carbon, and it can give us this compound. And let's say that there's also some acid, right? So let's say there's also some acid. But right here, we added a nucleophile. Now, Notice that my nucleophile is next to an alcohol, and notice that it's also next to a hydrogen. It's very reactive towards basically nucleophiles because hydrogens are very small, and this space right here is limited. The space between the oxygen and the hydrogen is limited. So the ethyl group has no problem going between the oxygen and the hydrogen. There's a lot of room to do it. It's very fast because there's a lot of space to do it. But if we were to do the same thing with this ketone, you would have this. Now notice that my ethyl group is attached between the alcohol and another alkyl group. Now alkyl groups have a bunch of hydrogens and carbons next to it. So it's getting clustered now. It's getting very cluttered, and it's going to have a hard time fitting between those grooves, right? It's a little bit of space now. So it's going to be slow because of sterics. Everything is because of steric strain. If we were to do the exact same thing with an ester, which is not very reactive, it's very bad, actually. Now, notice that it's between two oxygens, and these oxygens are going to be pushing apart each other like magnets. So if you have a magnet and you have another one, and you put them on like the same poles, well, they're going to be repulsive, right? They're not going to want to go together. So there's a lot of strain between these two oxygens, and whenever you put a nucleophile between those two oxygens, it's not going to have a good time. It's like going into a room of crowded people and getting pushed and pushed. Not good. Not good. And so an easy way to remember this is with the acronym that I made is CAKE. So CAKES. So this stands for aldehydes, ketones, and esters, and I really love desserts, so I just name it CAKES. The C doesn't stand for anything. Okay? So here's CAKES. Right there. I'm guessing like if you want to work with lithium aluminum hydride, then the carboxylic acid can be reduced with the lithium aluminum hydride. So the C does stand for something. In this case, it doesn't. But here we go. So aldehydes are more reactive than ketones, and ketones are more reactive than esters. And this is because of steric strain, right? You don't want to put your nucleophile in an area where there's a lot of hindrance, when there's a lot of electronegativity. You don't like that. So the next two segments are just very small and quick. It's just like kind of like general knowledge for the exam. In this case, we're working with 2,4-DNP, where DNP stands for dinitro phenyl hydrazone. So basically what this does is that it checks for alkenes and aldehydes. Okay, so it checks for alkenes. No, I'm sorry, not alkenes, but it checks for aldehydes and ketones. My bad. I'm sorry. So it checks for aldehydes and ketones, and it has an orange color. Okay, so similar to like some other reaction that we knew. I believe it was called a Jones reagent, where it was green, like a copper green. This reagent checks for aldehydes and ketones, and it gives an orange color if there is a ketone or aldehyde present. Okay, so just keep that in the back of your mind, and remember that if it comes up on the exam. Now, Tollens test is a bit different. Instead, it uses silver, I believe, nitrate. So NO3, and then 2, this is plus, right here. And it only checks for aldehydes. So only checks for aldehydes. It doesn't work for ketones. So no ketones. Except for the alpha hydroxyl ketone. So if you're going to use that in lab, yeah, you can use it. And the way it does it is that it's going to oxidize the aldehyde, right? And it's going to create pure silver on the test tube, okay? So I think that's pretty cool, right? It also converts aldehydes into esters. So aldehydes convert to esters. And the indicator that this completed successfully and that there were aldehydes in the solution is that if you look at your test tube and you see your reflection on like a little mirror, like on the side of the test tube walls, it's like silver lining, then you know that there were aldehydes present. That's what it's called, a Tollens test, aka a mirror test, because the walls of the test tube are going to be reflective, almost like a mirror, from the pure silver that has condensed because of the presence of aldehydes. And so me and Gizmo hope that you and your family are safe during this Gremlin pandemic. He doesn't mean any harm. He's just touring the world. He's enjoying his snacks right now, an Arizona tea and some Cheetos. He wishes you the best of luck on your exams. He loves you very much, and he's very proud of you. He's glad that you watched him learn with you, and that he is welcomed in your life. So thank you so much for watching. I'm really proud of you. I love you so much, and just know that I'm always here for you. So be safe and have a great day. Thank you.